Can you see my slides? Are the slides visible?
I think we're live. Yeah, I can see your slides. Okay.
Cool.
Hello, everyone, and welcome to yet another exciting live session hosted by AI Planet. We're thrilled to have you all join us for the incredibly insightful session. I'll start by introducing the speaker for today. We're excited to have Saurav Maheshkar with us. Saurav is a seasoned machine learning engineer with experience at Recourse AI and Weights and Biases. He is a Google developer expert in machine learning, conducts research on geometric deep learning and representational learning, and is passionate about open source. He also enjoys delivering talks and has achieved the status of a Kaggle 4x expert. In today's session, part of Summer Analytics Bootcamp by IIT Guwahati, Saurav will delve into the fascinating world of deep learning. We will explore the history of deep learning leading up to diffusion models, understand the mechanisms of training these models using modern day optimization techniques, and discuss various loss function formalisms. Additionally, Saurav will provide an overview of open source ecosystems around deep learning and guide us through a simple neural network implementation in JAX. Without further ado, let's welcome Saurav.
Okay, cool. Hi everyone. So again, as mentioned, I'm I'm based out of Manchester. I'm currently working at a startup called Lightly, where I mostly work with self-supervised learning in a commercial setting. I used to work at Recourse AI as a research machine learning engineer, and before that at Weights and Biases. I'm broadly interested in sort of geometric and representation learning. I love doing open source work, and I also like coffee. My socials are linked in the slide, so if you wanna ask questions after the talk, you can do that as well. So some notes before we start. This idea is borrowed from Subhaditya, but I will not talk about how AI has changed the world. I'm assuming everyone uses ChatGPT. Everyone knows the impact that it can have. We will take a top-down approach. We'll just focus on key concepts rather than focusing on I know theory or details. We'll take a code first approach. In my opinion, in deep learning, it is particularly valuable to just start implementing things, get your hands dirty rather than sort of focus more on sort of theory and definitions. I won't dive too much into the math unless needed. Obviously, more than happy to talk about it after the talk, but like we'll assume everything is smooth. We'll assume all functions are differentiable, all the spaces are measurable and whatnot. The slides and associated code is available on my website. Um, I believe that the link has already been shared. Uh, and yeah, so if you just go to my website /talks, you'll find the link to the slides. And again, after the session is complete, feel free to ask sort of off topic questions as well. Before I go on, let me try to check if I can adjust my mic. Is it better now? Shivaya, can you confirm? Okay, cool. So we have a lot to go through in an hour, so I will try to skim over some of the less important uh, uh, details. I have tried to sort of squeeze a lot of things into a 1 hour talk. This usually happens in like 2-3 weeks in a typical university course. I urge everyone to study each of these little topics in more detail as well. But first off, let's just talk about time. I think people underestimate sort of how new deep learning is, and it's always quite nice to like take a look back and see like how recently things started. One thing which I believe is very important to mention: ChatGPT is less than 2 years old now. So think about that. And yeah, so the first sort of few ideas regarding neural networks came way back in 1940s and 50s. Particularly, most of the research that was being done was done by sort of folks doing biology and psychology rather than traditional computer science, as we'll see later in the talk. Around 70s and 90s, we started developing much of the methodologies for training models. We started developing new architecture, CNNs. The MNIST dataset came out. That's one of the most sort of accessible vision data sets. And then preliminary work was being done on sort of NLP theory. I don't think I can do much about the mic though. Let's see. AirPods. Yeah. Okay. I'm sorry, but like this is the max I can do for volume. I can't take off my AirPods, because then there'll be a lot of echo. So please bear with me if the audio is not clear. Okay. So moving on. So in early 2010s, that's when we actually started doing sort of fundamental work in what we might call modern day deep learning. The ImageNet dataset came out. The AlexNet paper came out, which people mostly refer to as the ImageNet moment. That's when deep neural networks first sort of outperformed traditional neural networks, and that's also when the GPU revolution started happening. So those of you I know who play games uh, a lot would have sort of local GPUs on your machines, right? Uh, the foundations for that was still laid typically early on in 2010s. That's when sort of consumer GPUs started coming out. In late 2010s, we had stuff like GANs, beautiful work by Ian Goodfellow from MIT. That's mostly uh, responsible for all the deepfakes. Then AlphaGo came out. That's when we defeated sort of like the best player in the game of Go. Bird came out, which prior to I want to say 3 weeks was mostly responsible for the Google search algorithm, and then from 2020s up until currently, we saw the Transformers paper come out, we saw diffusion models come out, we saw state space models come out, and so on. Now, apart from theory, I also want to talk a bit about the tooling. Like as I said, we'll take a top-down approach. So it's important to understand since when like, we have had like a nice open source ecosystem regarding this as well. Okay, in early 2000s, so correlate that with the theory timeline, right? Uh, the first sort of Torch, CUDA, and Theano APIs came out. These were mostly in sort of C, Lua, relatively sort of I want to say non-beginner friendly languages. In early 2010s, Cafe came out and TensorFlow 0.1 came out. So that's when Google sort of entered this whole ecosystem. In late 2010s, that's when sort of the Python side of the ecosystem stabilized. PyTorch 1.0 was released, TensorFlow 1.0 was released. The first Transformers library by Hugging Face came out, Spacey came out. And then currently we have JAX, which is what we'll use for most of this talk as the code example. JAX came out backed by Google. That's their new sort of state-of-the-art ecosystem. It's accelerator agnostic. It has really good sort of vector computation. We'll cover that in the talk as well. Streamlit and Radio came out, so that's these are like really easy to use Python libraries to create UI for your various apps. Diffusers came out again by the team at Hugging Face, and then recently Mojo came out by the original creators of Swift and the whole ML IR ecosystem. Now, that's the timeline, and then again, we are talking about like relatively recent things, right? We're talking about 2010s. Uh, Compared to like most other sciences such as physics, that's relatively very modern. Um, but yeah, so what is deep learning in the first place, right? So usually it refers to the practice of training neural networks, very big, to learn representations of some given underlying data distribution. This is the sort of the definition which I like to use. It's very loose. It doesn't specify much, but I like it that way because it also generalizes really well. Now, there should be two new terms for you: neural networks and representations, right? We'll cover neural networks later on, but they're just loose mimicry of how our human mind works. And then representations. Representations, as the name says, is just some sort of vector or numerical form of expressing some given data distribution, right? But what do you do with it, right? So when I was creating these slides, I thought about, okay, what example could we talk about? And I watch football a lot. So one particular question which someone might think of is, how do we statistically determine which team has the most chances of winning a given league, right? You could take football, you could take the IPL, you could take F1, whatever, right? These are like some of the tasks that we could work on. For the football example, particularly, let's see. So, who wins the league is determined by who has the most points. Okay. Who wins the most points is determined by who wins the most number of matches. And I think it's fair to assume that the team who wins the most matches is the team who scores the most goals, right? So again, that is one particular data point which you can use to uh, determine who has the most chances of winning. There are, of course, other factors as well. Player fitness, weather, infrastructure, momentum. Again, you can consider sort of various data points as well. And again, they don't have to be numbers. Expected goals is a number, but you could add in sort of video information as well. You could add in text information as well, right? Like how confident are the players in the post-match interviews? You could add images as well, right? Are there sort of new skills and tactics being shown on the field? And again, that could be a video stream as well. So various modalities for us to consider. Going on with sort of our expected goals data point, this particular graph shows that, okay, some city players have a large number of non-penalty goals, like expected non-penalty goals and expected assists per match as well. So, again, if you plot these out, there could be like a rough correlation to saying that Manchester City have the most stats when it comes to expected goals, right? Again, you can draw various plots like this. I'm sure there would be some rival fans who will pull up some other statistics as well. But again, it depends on like how you evaluate your model, how to score it. Another thing to consider is the training time and the carbon cost. People forget this when we talk about modern day deep learning is the carbon output for training most of these models, right? GPT-3, for instance, consumed as much carbon as it would take for someone to drive to the moon and back. When you train models on Colab, think about the carbon cost. When you consume sort of a lot of these models by a lot of different companies, think about the cost it incurs as well. But again, why do we do this? Why do we use deep learning in the first place? I'm sure folks who came on to talk uh, before said about, I don't know, regression models, Gaussian uh, modeling. Why do we need neural networks? We need deep learning. Now, we have traditional algorithms which work well. For instance, we can see for I know this is an example for dehazing, deblurring, denoising, right? We have algorithmic solutions which work well. Why do we need deep learning in the first place? Well, we don't have solutions for tasks like this, right? What if we want to do simultaneously segmentation, object detection, labeling as well? Right now, you can see we're doing segmentation for recognizing which part of the image is a car. You're doing detection for recognizing if it's actually a car or not, and then you're doing labeling on top of it as well. like what the particular object in the bounding box is, right? So we couldn't develop algorithms for things like this, and if we could, it was not worth the effort uh, that the people put into it, right? We want automated solutions. We want general algorithms which work well for most tasks, because then the trade-off makes sense. Now, again, so what can we do with these representations? These representations can then be mapped to any sort of output distribution. Now, what do I mean by this? And again, this is the reason why most people say neural networks are black boxes, right? So you have your data in some form, you do some training mumbo jumbo, and then you have a trained model which makes an output, right? But what we don't know is why does it have like a particular configuration of weights, right? That's why most people call it a black box. You put something in, it gives out uh, an output. And again, there are a lot of smart people who are working on this. It's called XAI. But yeah, again, this is why people refer to it as like black boxes, because you put something in, it just spits out an output, but you don't know exactly why. Okay, but like, what can we do with it? This is perhaps an example that you might have seen before, which is sort of clustering and labeling, right? So assuming your data distribution initially looks like the one on the left, where you have some samples from for any given tasks, you train a neural network for it, and then it gives you the output in different classes. Now you might think that, I don't know, KNN might be like a very good way to go about this. Um, One particular example I would like to give is think about Pinterest, right? You found an image and then you want all the related images for it, right? It shows related pins. Now, if you were to use KNN, what it would essentially do is once you pick an image, it would go through every other image in the Pinterest database, compute its relative difference, and then give you, I know, the top K matches. Now think about the amount of compute even that would take. Assume the image to be, I don't know, 1920 1080 colored image. That's at least, I know, on the top of my head, 10 to the power 7 sort of dimensions. Then you're computing the difference using whatever metric you have, and then you're doing that over all the given images. At that point, the trade-off of simplicity is not worth it. What you would rather have is already have sort of like a pre clustered distribution where you can just result like, I know, the top K searches. This is another thing which you could do. So given pixels in uh, locations in 2D space, you can map them to a color in 3D space. Now, this particular formalism comes from a line of work called Nerves, which allow you to generate 3D models from a few number of 2D images of various angles. So, I don't know, imagine you want to recreate a 3D model of a car, right? You take, I don't know, 30 images from various angles, and then you can train one single neural network to then take those 2D images from various angles and get one single 3D model out of it. Again, that's another thing you could do with these so-called representations, right? Uh, these slides are borrowed from the Google research team, who highlighted like how JAX internally powers a lot of work that Google and DeepMind does. Particularly of interest might be the one on top left, uh, where they use sort of transformer models and attention to solve, again in quotes, protein folding. This was big in news, I think, I'm going to say a year ago. And then in top right, you can see sort of traditional text to image results. In bottom left, you have sort of work in traditional molecular dynamics and simulating n-body systems. JAX is used in that as well. And then you can also use it to sort of do work in physics. So if you go to the slides, you can access that link and see how people are using JAX to solve sort of some of the traditional problems in quantum mechanics. And again, this is software which was originally made for the deep learning ecosystem, but it has had sort of impact in traditional sort of work in chaos theory, dynamical systems, and physics as well. Now, let's get to like what actually neural networks are. So, neural networks are DAGs. So, those of you who have done work in data structures and algorithms would know the term. So, directed acyclic graphs. So, all neural networks are essentially DAGs. It's just that they have some quote unquote biological origins, right? Now, before we introduce what neural networks are, I think it's important to talk about what the neuron is. Now, the computational neuron is called the perceptron. Um, and again, as I said, the fundamental work behind the computational neuron was actually done from researchers in psychology. So, if you see top left of the paper, it was published in Psychological Review way back in 1958. It's quite a easy read. If some of you want to read it, just like sort of ignore the psychological and the biological terms. It's simple 10-14 page read. Quite interesting what people thought of sort of groundbreaking back in the day. Now, so um, on the bottom you can see a biological neuron, and on the top we have what we now call a perceptron, or like a computational slash artificial um, neuron. The image from the bottom should be familiar uh, uh, to most folks. I think we had this in high school biology as well. So the neurons in the way the neurons are structured is that they take inputs from various other neurons in sort of the main cell body. They transfer the neuron to other neuron using what are known as axon terminals, and the transport in the middle, that's where sort of most of the smart stuff happens in our human minds, right? They have sort of I think they have other cells on top of it which translate the electrical impulses in various ways. But yeah, so if you keep the figure in the bottom at mind and see the figure on the top, so we have a very similar structure. You have inputs coming in from various sources. Uh, let's say inputs are labeled x1 through xn. So for each different input, we have what are known as associated weights. So I know for the task, if let's say again, let's go back to the football example, right? So um, the number of expected goals has a much higher weight when it comes to who wins the league when compared to, I know, the color of the jersey, right? So uh, that particular data point has a lot more importance when it comes to the task that we want to establish compared to the color of the jersey. So that will have a higher weight, right? So we need things like this to determine like what input has more importance when it comes to our task, right? So you take the weight for that particular input point, multiply it with the value that you're getting. That becomes like one that becomes your input from the one variable. You do that over all possible variables, so you have a summation over all wi xi, and then we add what's called a bias term. The bias term essentially is there to sort of provide support for the errors that we'll get. We'll talk about the bias term later on as well. But essentially, you take the input from various sources, compute this thing. So the summation of wi xi plus an additional term, and then we apply what's called an activation function on top of it. Okay, very closely similar to our understanding of the human neuron. Take input from various sources, do something, and then make an output. And again, I want to reiterate of this. This is based on a loose understanding of a neuron. Again, this work was done way back in 1958. Now we know a lot more about the mind. Uh, for instance, we have things like, I don't know, neuroplasticity. That's how human minds are able to unlearn and relearn things. Neural networks can't do that, right? So again, these are loose approximations of our human mind. The closest approximation that I know of is the work being done by Steve Ferber over at Manchester. He has a lab in the University of Manchester where he has, I think, by this point, over 100,000 chips just trying to simulate uh, the mind. That work is called spiking neural networks, and the work is called Spinnaker. If you want to look that up, that's an interesting sort of approach as well. Okay, so now that we have a loose understanding of what a computational neuron is, let's extend that neuron to a neural network. So you have various inputs. For each of the input, you have a bunch of weights. You compute their sum which is like sigma wi xi. You apply a non-linearity on top of it. That's the activation function, and then you get the output. The only thing of importance here is why the non-linearity. The choice of the activation function is what differentiates neural networks from, let's say, a simple polynomial regression model, right? That, again, remember, it's polynomial linear regression, right? What you're essentially trying to model, even with sort of non-linear models as well, but most sort of underlying data distributions will be non-linear. There is not like a simple correlation between data points. So the non-linearity or the activation function is the key thing which sort of differentiates neural networks when compared to traditional approaches. And particularly why it's helpful is there will be a series of sort of when you see the whole output, it has a sort of a series of non-linear activation functions on top of it. Now, one key notation here is instead of taking single inputs, we will consider vectors. So if you remember, the equation before was simply just summation over xi wi. Right now, what we're saying is instead of summing over everything, you just store the various inputs in a single sort of vector, and then instead of doing single sort of uh, multiplications, you're doing it all at once. Now, why do we do this? It's because we have computers now, right? Vector multiplication is inherently faster. That's why, like Python is considered to be a fast language when operating with vectors and matrices, right? There's the notion of list comprehension. Everything is faster if you do it via like a vector or a matrix uh, notation. So instead of summing over, you simply have like x transpose w. So you are essentially computing the output now in a cumulative manner. Instead of taking single inputs, you are considering all of them at once. Now, let's extend our definition from a single neuron of a single neuron with single output to various neurons with various outputs. Right. The first step for that would be a single neuron with multiple outputs. So just look at the figure. Instead of having one output neuron, now we have two. Instead of doing the calculations one, we'll have to do it twice. One for each output neuron. So instead of going from x1 to a single y, it's going from x1 to z1, x1 to z2. Similarly, x2 z1, x2 z2, and you'll do this for the number of output neurons that you have, right? Okay, we have just gone from uh, a model of a single computational neuron, so that's one neuron with one output. Now we we still have one neuron but with multiple outputs. Now let's extend that to multiple neurons and multiple outputs. Again, what we have simply done is just added another layer of computations to do, right? So this is where the concept of layers come in. Assume you have inputs x1 through xm, and then you have a lot of sort of intermediate neurons z1 to d subscript 1, right? And what you essentially do is calculate the intermediate outputs of the neurons and then carry it forward, right? So the output for z1 would be x1 w1 x2 w1 so on up until xm w1. You compute that sum, you pass it through an activation function. That becomes your value for z1. Then your final output would then be z1 y1 z2 y2 z3 y1 up until sort of zd1 y1. And then again you compute um, the output, apply a function, and then that is your final output. Uh, in the bottom, you'll see in the notation what's highlighted is sort of the layer index. So for each particular layer, you'll have different weights, right? The number of weights in each layer is easy enough to determine. It'll be um, inputs of the layer into outputs of the layer. Now, let's talk about the activation functions in some detail as well, right? How do we choose them? You can go as simple as using a linear activation function, which does nothing. Okay, sorry, you'll have to excuse my dog. Yeah, so for some given input, the linear function just outputs the same thing. You can also have the signed activation function, which if you get a negative number, it results in -1. If you get 0, it results in 0. If it's a positive number, it results 1. Now, these sort of activation functions are not usually used in practice. What's usually used is either the sigmoid, the tanh, or the relu. Uh, what the sigmoid does, it essentially normalizes the value between 0 and 1, right? It makes a smooth curve. Why do we need a smooth curve? That'll come up in later slides. But yeah, another variant of that is the hyperbolic tangent or the tanh function. Again, instead of 0 and 1, it normalizes it to -1 and 1. You also have the ReLU function. This is what's typically used in transformers. What that does is if it gets a negative number, it just results in a 0. Or if it's a positive number, it returns the number itself. ReLU exactly is not used. Variants of ReLU are used, such as Gelu, Sui Gelu, I think G Relu as well. Again, there are sort of mathematical tricks which you can use, which stabilize training and give better outputs. If you want to have a look at the various activation functions which are usually used, I would advise for you to go to that link and check out the activation functions which are available by default in the Flax library. Okay, so now we have another sort of essential topic. I've called it checks and balances, but I'm referring to the loss function, right? The reason I've called it checks and balances uh, is that when people say loss functions, they're usually referring to sort of supervised learning. Supervised learning is not the only variant of deep learning out there. There are other things. There's unsupervised learning, there's self-supervised learning. That's what I do for a living. There's semi-supervised learning, there's reinforcement learning, right? There are a lot of different variants out there. But essentially what we're trying to do is establish sort of is a network performing well or not? If it's not performing well, how bad is it performing? If it is performing well, how well is it performing? Again, just try to get the essential gist of it, right? It's just checks and balances. If the model is doing something wrong, we will correct it. If it's doing something correctly, we'll sort of reward them for it. Now, I will just like, for example, let's go over a couple of loss functions. So, and if you consider the task of regression, when people say regression, they usually refer to determining a numerical value. One example task might be like, what is the temperature going to be tomorrow? Again, that'll be a number. So, a commonly used tasks for regression is the mean squared error. So, it computes the difference between what we know is the truth value to what the model outputs. It computes the difference, squares them, does that for every sample, and calculates the mean, right? So, it's the mean squared error. For classification, what's commonly used is the cross entropy loss, what you see on the slide. The example, will it be cold or hot, is a binary classification task. So again, you only have two things, either cold or hot. We obviously know there are a lot more seasons, but yeah, so you can extend the sort of that definition to be, I know, what season will a particular date be, right? So then you'll have a lot more classes. The commonly used loss function for that is the cross entropy loss. How it works is you take the known truth value, multiply it by the logarithm of the expected value. Now, why is log there? Again, it makes the training more stable. It has mathematical properties that we can exploit. And again, it has sort of a basis in our sort of theoretical knowledge of statistics as well. Uh, Cross entropy is usually the statistic that we use to compute the similarity of two given probability distributions. So again, if you do sort of work in sort of traditional statistic methods, you'll understand why we use things like, I don't know, log or the exponential in this. Now let's go on to understanding what optimization is. We're thankfully running well on time, so I can talk a bit more about the implementation side as well. Now, before we get there, I want to motivate why we use checks. A lot of people don't recommend this as the framework to start on top of. I would advise, if you're starting off, please put some effort into jacks. It might be uh, sort of difficult to get started with. It does not. It does follow sort of the traditional object-oriented paradigms, but it has a functional aspect in it as well. Most people don't like sort of the functional way to go about things. Like I can totally understand why, but the things that Jax offers make that trade-off worth it. Now, again, let's go through a very simple example of what we talked about, but in pure sort of NumPy. Right. NumPy is a library in the Python sort of ecosystem to do numerical computations, if people don't know. So, given our weights, that's the parameters, and given some input values, what we essentially do is, again, think about what I talked about after I introduced the neuron, right? So we have a vector representation. So you compute um, x transpose w, and again, because we're talking about vectors, it's not a simple piecewise multiplication. You are computing the dot product between the two vectors. So you do numpy dot dot, add the bias term, compute the output of the activation function. In this particular example, we use tanh, and then we just return that. So again, this is like a very simple function which determines the output of a given neuron, right? And then we have an another function which computes the loss. So for any given batch of data, you get the inputs and the targets. You feed the input into the model, and you get the output for the model, and then you just sum over everything. The you sum over the square differences. right? So this is an implementation in pure NumPy. So what's wrong with this? Not much if you're working with a few samples, but what if you're working with a large number of samples and you want to run on hardware? This particular piece of code is not optimized to run on GPUs or TPUs. Right? NumPy was inherently written to sort of traditional CPU workloads. We don't have optimizations because later on, as you'll see, we'll need to compute the sort of the derivatives of each of these functions. For instance, if you want to compute the derivative of mean squared error, that's still relatively easy, but the loss functions will get complex. The way your model computes the output will get more complex, and in order to compute its derivative, you'll need to do a lot of hard work if you're just using pure NumPy. It doesn't so pure NumPy does not do some sort of compiler heavy tricks, right? For example, as you can see, I've written compilation fusing of operations. Folks who have taken sort of a class in compilers or sort of programming language theory or even hardware, you'll know that the key difference behind GPUs is that it has sort of specialized operations on a chip level. So instead of computing the summation, so instead of uh, multiplying something and then computing the summation, it can do everything in one single CPU operation, taking one single CPU cycle, right? NumPy inherently does not exploit that. And this code is not parallelizable by default. You can't just say like run on 8 cores using 8 workers. It will not exploit all 8 cores and all 8 workers. So where do we go from this? Now, JAX has a very simple sort of NumPy API. So instead of importing NumPy as NP, you can import JAX. So just by doing, instead of doing NumPy, if you do JAX dot NumPy, you'll automatically get a lot of sort of improvements. Just by doing this, if you run this code on some specialized hardware, it'll use the underlying GPUs and TPUs just by, again, changing what module you're using. Now, if you want to compute the gradient of the function, and if you did not have JAX, you would have to manually determine it by hand, write that in code. That'll be another function, and then you will use it later on. If you're using JAX, it has a function called grad, which simply takes a Python function or a callable, and then it automatically computes its derivative. Now, what else? Can I vectorize this? Yes, you can. You have this thing called vmap, which vectorizes any sort of callable across a number of cores. And again, you can pass in the derivative which you got as well. So again, these are sort of composable things which you can use. Can you compile them, right? The key difference between sort of the reason people say Python is slow when compared to C or Rust is that it's not a compiled language, right? So it'll obviously be slower because there's sort of another daemon which is running alongside Python to actually run the code. Well, there's this concept of JIT, just-in-time compilation, which which takes out snippets from your code which don't change much, compile it, and then the next time you call the function, it automatically knows what to do. So it just takes sort of the pre-computed state and uses that. So without changing what you had before, if you just apply the JIT operator uh, on top of it, you are sort of inherently using compilation as well, right? Now, there's one more thing which is called pmap, which allows you to parallelize it as well. So first we vectorized it using vmap. So if you had something which only works for one given sample, you can generalize it to work with any given sort of number of input dimensions by using vmap. So you vectorized it. Instead of taking one sample, it now takes a vector. And then you can parallelize it. So it can work across multiple sort of GPUs, CPUs, cores, and whatnot. And the way you do that is by using PMAP, right? Again, you don't have to change the code at all. You just have to sort of use these sort of composable functions which JAX offers you. And automatically you have parallelized it, you have vectorized it, you have compiled it. And this particular same piece of code will work on CPUs, GPUs, or TPUs. Now, the key ideas behind JAX is the Python code is sort of traced to an intermediate representation, which can then be used by their automatic sort of differentiation libraries. Um, and because JAX has its own IR, it can do domain-specific compilations. So that's work done by the XLA compiler team over at Google. It has a familiar API, as you saw. Instead of doing NumPy, we just imported them as JAX or NumPy. And again, it has a powerful set of composable transforms, right? So grad, JIT, VMAP, PMAP. There are some other transformers as well. For instance, there's remat. I believe there's another new one which has sort of automatic logging as well. And again, JAX was designed from the starting around XLA. XLA is sort of these new accepted intermediate and compiler standards for all hardwares. So even if you're not working with NVIDIA hardware when it comes to GPUs or Google hardware for TPUs, even sort of LPUs, right? There are a lot of these accelerator variants. If all of them just stick to like the XLA standards, JAX can in theory run on all of them. How to get started with JAX? The official JAX documentation has a lot of good sort of collabs uh, to understand how the library works. They are a bit finicky. They are not machine learning focused because obviously it's meant to be sort of a traditional computation numerical um, library, right? So as you can see, they have explanations on how random number generation works in checks. How does JIT work? What the intermediate representation is. Again, if you just think about what you ideally need to do is just think about quick start, go through the official flags tutorials, and that should be enough to sort of understand how to get started, and then just start building models. You'll run into error. Go to Stack Overflow, ask ChatGPT, go to GitHub and look at examples and then learn. Don't focus too much on theory at first. This is for both JAX and deep learning in general. Now there are a lot of libraries in the JAX uh, ecosystem for various tasks. For like deep learning in general, there's Flax, Haiku, and Trax. Flax is now sort of the well-known standard for neural network for building various models. Haiku was the library that DeepMind initially used, but again, they use Flax now. Trax was also used by the Google Brain team, particularly for some of the earlier transformer um, models. All of them use Flax now. For optimization, that's particularly Optax and JaxOpt. So these libraries contain implementations of the various sort of optimization functions, right? If you've heard of Adam W, Lars, Shampoo, Lion, there are a lot of them. Mostly people use Optax now. JaxOpt is used for sort of non-deep learning optimization research. And again, there are many more uh, uh, libraries made by Patrick. He has his own sort of beautiful ecosystem all in JAX as well. Now, let's quickly run over sort of optimization and an example code as well. But again, I hope I have at least motivated some of you to look into JAX when, as compared to sort of Keras and Torch. Now, um, if you remember back to what our loss function did was, right. So For any given input, a loss function gave you one single value, right? How wrong or how correct is your model? It takes in all of the inputs, it multiplies that by the weight, adds the bias, applies the activation, computes the difference, blah, blah, blah. But essentially what it does, it gives you a value for a given value of the weight, right? Again, the loss function depends on the weight value. If you change the weights, your loss will be different. Again, for the task of who wins the league, if you have more weight to what color of the jersey wins the league as compared to who scores the most goals, obviously your model will perform badly. However, I think more blue teams have won the league, but that's just a lucky thing, I guess. Uh, uh, but then again, it gives you one single value depending on the weight. So if you plot the value of the loss function over time, you get what's called the loss landscape, right? This particular uh, image is a 2D version of a surely sort of higher dimensional loss landscape. Because even if you have sort of three weights, for each different possible value of those three weights, you will get different loss values. So that'll be a 3D surface, right? But you obviously won't have three weights, right? More sort of modern, like I think GPT-3 was suspected to be around, I want to say 1.8 billion or something. So again, the space in which the surface lies is all possible values of 1.8 billion, right? And again, that's in the real number space. So again, just assume the mathematics is smooth. Assume you have an n-dimensional smooth surface which does have a minimum. Assume all things are nice. Assume math is not being rough with us. So you will get this surface. And what we essentially want to do is get the most minimum value of the loss function, right? You want your model to be incorrect the least, therefore the least value of the loss function. So it all boils down to finding the minima of some given n-dimensional surface. Let's just consider 2 dimensions for now. But then again, you can't use sort of traditional methods which we learned, I know, in high school, right? You just compute the derivative set it equal to 0. You'll get sort of these turning points, calculate the value at all turning points, and then you'll get the minimum, right? You can't use these things because, again, when you scale to a billion numbers, computing the derivative is tough. Setting all of them to 0 is tough. And as you saw, we have things like the logarithm, we have things like the exponential, and you can have log within the log, right? So computing these by hand is not really efficient. What we instead do is do gradient descent. Now, this was originally supposed to be a video, but I think StreamYard is not being nice with me. So I will try to explain this sort of using words. So imagine uh, you start off at the yellow point, right? We determined what the equation of the line is at that given point, right? So you'll get the slope. And what you essentially want to do is move in the direction of the negative slope, right? For this particular yellow line, you will get a slope which sort of uh, points in that way, and you want to move in the negative direction because that is in the direction for which the value of the function is minimum, right? And you just keep doing that over time. It's as simple as that. You pick a point, determine what direction you have to move in, and then move in that direction by a particular factor, right? For a particular given what's called the step size. It's as simple as that, right? That's what we use to sort of train neural networks. Essentially, there are of course sort of a lot of nice mathematical tricks which modern day optimizers use, but it all comes down to that. Determine which direction to move it and take little steps until you eventually hopefully reach to a minimum value. Now, there are no sort of theoretical guarantees which will tell you that you have reached the global minima, right? It it will most likely be that your model has reached a local minima. People have reached sort of global minimas, but using toy examples like 10 dimensions and like a perfectly sort of a well-sampled data distribution space, but that is not how the real world works. In most sort of real life use cases, your neural networks will have converged to a local minima, and that is fine, right? ChatGPT is a very good model, and that in most cases has reached a local minima, right? Just be fine with the local minima. Again, don't delve too much into the math side of it unless you want to work of course in sort of theoretical machine learning. I know a lot of folks who are just trying to determine how to like reach the global minima always, but that's like a long standing problem in maths and in sort of optimization theory. uh, Now, how we sort of propagate these values backward, that's done using an algorithm called the backprop. We don't have much time to cover this. Even if I had like a whole hour, it would not be enough. This usually takes like weeks in a typical sort of college course. So spend some time learning about what backprop does. But essentially, it's just one way to determine uh, the the derivative going all the way backwards, right? Like going backwards through the network. Um, okay, cool. So let's walk through a code example really quickly. We have 4 minutes. It seems again, slides are on my website. If you look up my name, go to talks, you'll see the slides there that has the example sort of notebook as well. But again, really simple setup. We will train sort of a small multi-layer neural network using small step sizes. We'll only train for 10 epochs and so on. Cool. So you need some way to initialize the weights of the network because again, even though it is a vector, it has to start from somewhere. In most cases, people have what's called a normal distribution. Uh, you could use Gaussian, you could use Poisson, whatever, but most generally Gaussian and normal distributions works well with some engineering tricks. That's where you have sort of Zapier initialization, calming initialization, and so on. But again, assume your weights are initialized to some particular random value. These two functions take care of that. They do have sort of a lot of list comprehension, but just assume they do what the function name says it does, right? So we have initialized our network with some given parameters. We will use the relu function. And again, just if you remember back from the activation slides, it's simply the maximum between 0 and x. If x is negative, it'll give out 0. If x is a positive number, it'll give out x. That simply becomes our relu function, right? The way we sort of compute an output from the model, given an image, we will work with images in this particular instance. You you calculate weight times the input, add a bias term, pass it through Redu, right? And then I've also added sort of another bit in this where it does that with like every particular given sample via log sum, right? So you have that particular term to use in the loss function within this example as well, within this function as well. You can obviously do it in another function as well. It just makes for like a smooth sort of output. Now, when I'm talking about that, I mean the logics, right? So let's check if the function works on a one single image. So you create a random image of size 28 cross 28, one dimension, so sort of black and white. Pass that through our function, and then you'll get one output of shape 10. Why shape 10? Because we're considering the task of classifying an image into 10 different classes. The output of a model is 10. Why 10? That is defined way back in our hyperparameters. So the number of target variables we have is 10. Good. So it does not work on batches yet because we have not used bmap, right? So if you try to pass in a batch of data to this function, so if instead of giving one sample, you give 10 such samples, it won't work. However, just pass the function into bmap and then try to do the same thing. Now you'll get 10 outputs of size 10, right? Again, just use VMAP handles batching. Very easy to work with. Again, you have some helper functions which calculate the loss, which update the weights of the model, which compute the accuracy and so on. We one hot encode the inputs. If you want to know about what one hot encoding is, I have attached a link to an article, but a simple Google search should be enough. We will use the MNIST dataset for training. That's a collection of images for the task of classification. You can use sort of TensorFlow data sets within JAX as well. And then for every given sample in the batches, um, you update the parameters of the model after computing its loss and so on, right? And then you can get the corresponding sort of training and testing accuracy. And I would advise all of you to have a look through the example. There are a lot of other examples available on GitHub. I have published a bunch of Colab notebooks, uh, creating a sort of template if you want to do image classification in Jackson Flags, along with Soumik Rakshit. There are a bunch of great notebooks available on the UVA website as well. UVA, just three letters, UVADL. But yeah, again, let's get to questions. I saw a number of questions in the comments. So
Yeah, I'll add them to the screen.
can a single layer neural network take text input as well? Sure, in theory, yes. So I know, for instance, let's assume I know your text is hi, my name is Saurav. Hi, my name is Saurav. So that's 5 words. Assuming you have a numerical representation for each of those words, you can assign different weights to each word, and then one single layer neural network can take a text input as well. Mostly text is a more complicated thing, right? Because again, words have meanings. You can't just simply convert them into numbers and expect to get good answers. That's why we have the whole theory behind, I don't know, tokenization, encoding, and so on. But yes, in theory, a single layer neural network can take text input as well. Hope that answers your question. When to use tanh and when to use sigmoid. Um, so again, determines at what point of the neural network you are using it. Sigmoid normalizes it to between 0 and 1. So if you want your output to be between 0 and 1, just use sigmoid in the last step. Before that, you can use tanh, or if you want your output to be between -1 and 1, you can use tanh there as well. Typically, it depends, like there are well-known sort of activation functions depending on what domain you're working in. Text, for instance, usually uses, I think, swigelu or something, SWIGELU. But yeah, again, answer as in for most cases, it depends. Is it possible to use Keras with Jax as well? Also, how is it different than TensorFlow? Okay, that's a good question. Yes, it is possible to use Keras with Jax. In particular, it is possible to use Keras 3 with Jax. That's the new rewrite. The new Keras 3 rewrite is compatible with PyTorch, TensorFlow, and Jax. All three at once. You just set what backend to use. Have a look at the official the Keras repository for how to do that. I'm assuming the question is how is Jax different than TensorFlow? Jax is supposed to be much okay. Think about Jax as a variant of NumPy, right? So it's inherently very different from TensorFlow. I hope that answers your question. So just think about Jax as like a more modern version of NumPy. What is more better to compare TensorFlow with is Flax, which is the official sort of the deep learning framework to use. And the answer would be TensorFlow is based on NumPy, Flax is based on Jax. Sometimes when I use JIT compiler functions in JAX, it is pretty slow. What is the reason? Yes, that does make sense. So just you can't put JIT on top of everything because maybe like I don't know if your function has a lot of like if and case statements. Obviously, the way JIT compilation works is if usually for one given input you're getting the same output, it it freezes the way it does the computation, right? So in neural networks, mostly for different outputs, you will get different answers. So JIT doesn't blindly work everywhere. There are very particular instances where it does work well. Again, examples can be found in the official Flags repositories, but you can't just throw JIT on top of everything. There is a decorator which you can, however, use, which does it automatically. But again, that does not work every time, and obviously the first few runs will be quite slow. But once it figures out where to use JIT, it's quite fast. Yeah. How does a choice of activation function affect the training dynamics and performance in different applications? Um, I'm assuming you are asking from like how, as in like tell me how rather than explain why it does that. But like for text in particular, there are some loss functions which are better suited for the input values that you get. For instance, in text, most sort of input is from their representations in some sort of dictionary, right? So um, the input values are bounded. Like there are only a maximum number of sort of words you can have in a vocabulary. So your input is inherently bounded. It is inherently integer in value, right? I know. Hi, my name is Saurav. All of them are unique words. They will have sort of 0 to 4 in integer mapping. So there are like when I say it depends, it's like it really depends on sort of what the input and output values are. In vision, for instance, it's really common to use what's called the mesh activation um, uh, function. Why? It's because it's capable of sort of retaining small steps as the neural network gets sort of more deep. Again, it depends on what task you're doing. It depends on what architecture you're doing. The easiest way to determine what activation function to use, figure out what task you're doing, figure out what architecture you're doing, look up what the current state of the art is, and use their exact activation function. Yeah, hope that answers the question. How do you approach the design and tuning of a neural network for handling high dimensional data while avoiding the curse of dimensionality? Again, I'm sorry, but it depends. Um, uh, yeah. So usually for design and tuning, the curse of dimensionality is nowadays uh, sort of ignored because we have a lot of mostly we have a lot of available compute even compared to data sets. For instance, um, beyond ChatGPT, most models now use sort of synthetic data samples. So we already have as much compute as is needed to train over all of the knowledge that human beings have created on the web, right? So the curse of dimensionality is nowadays not really talked about. Where when it comes to like how do you approach design and tuning, you pick up the most state of the art sort of architecture in today's day and age. That would either be transformers or diffusion models, state space if you're feeling confident, CNN if you wanted to sort of if you actually want to sell your service. As far as tuning concerns, again, there are state of the art optimizers which you can use. Again, it just comes to like reading what the current best paper is and mimicking their sort of training recipe. But yeah, I'm sorry, but the answer to most of these questions is it depends on a Google search.
Okay, it's the last question we have for today. Yeah, that's it.
Cool. I have worked with JIT. I don't have clarity on VMAP. Can you show one example? Okay. I on the slides particularly, I only have this particular example, but then again, okay. So let's go back to the way we have made a function, right? Um, this function is meant to be used with only one single input. That input can have any number of dimensions. For instance, it's an image, but it only has one image, right? So just write all of your functions as if it's meant to be working with one given sample. Um, and then just apply VMAP on top of it as I've done here. Simply put VMAP on top of it and it should work. The second parameter in axes, that means so after which dimension do you pad? Okay, so this might require explanation. So the output for this is 10, 0, right? Our output dimension was 10. If you want to vectorize this, you will have to specify where the extra dimensions come in from. In axes, we specify where those extra dimensions are. None, 0 just specifies that all the extra dimensions will be before the actual sample. This in axes can be a bit finicky to work with, but for most example sort of tasks, like most general tasks, you should find examples in either the transformers repository or like any of these research paper code bases regarding how to use VMAP. Just try a bunch of things, it'll work out. It's typical coding: try, fail, Google, repeat. So, yeah.
I think that's it with the questions. That brings towards the end of the session. So thank you so much, Sawyer, for the insightful and comprehensive session. Before we wrap up, do you have some closing thoughts or additional advice for the participants?
Again, try to take a top-down approach. Don't think too much about theory definitions. If you remember what particular concepts mean or not, just try to do as many examples as you can. Try to implement as many papers as you can. Try to train as many models as you can. Try to take like a code first approach. Eventually, you will just get it. It's not a math heavy field. You don't need a lot of math, and if you do, it is quite easy to pick up. Again, unless you want to do work in sort of the mathematical understandings of it. I started working in deep learning when I was in 12th with sort of basic understanding of how calculus works. You just need sort of basic Python, basic math. Just start implementing things and you will get the hang of it. I can't highly recommend the Fast AI course enough. It is free. The recordings are online. All the sessions have been recorded with all of the content online. They have a great community as well. Try to do that course if you have the time. Uh, the machine learning ecosystem relies heavily on open source. Try to contribute to open source if you can. That has been the most sort of helpful factor in my career as well. Yeah, that's it. And one advice: if you have to set the random seed, always set it to 42. It just works. Trust me, it just works. Yeah.
Okay. Thank you once again for sharing your knowledge and experience with us. Your contributions have made this session incredibly valuable, and thank you for watching, everyone. Yeah,
Thank you,
that's it.
folks.
Thank you.